Hi, this is Alex Galt with Edina High School. I'm looking at 113 today, which is about removing discontinuities. Either you're going to be removing discontinuities by fixing a removable discontinuity, or you're going to be changing parameters in a piecewise function to make a piecewise function continuous. So for removable discontinuities, if we look at that continuity test, which is that three-part test, part one might pass or it might fail. You might have a value or you might not. So you can have a removable discontinuity that has this is a removable discontinuity. It can have a value or it could not have a value. Either way, it's a removable discontinuity. The limit as x approaches c will definitely pass. If it's a removable discontinuity, that is for sure true. Your limit will exist. The place where your continuity will fail is your limit will not equal the value of your function, if the value of your function even exists. So what you're going to do to fix that problem is you're going to take that f of c and redefine it so that it's equal to the limit. So here's an example of a piecewise function. Well, it's a function that has a rational function, but it doesn't exist at x equal 2 because there's a hole there. So it's defined as b when x is equal to 2. So the way we fix this is we say, well, we know that so for part one of that continuity test, we know that f of 2 is equal to b. We know b exists, so that's a good start. Now for part two of that continuity test, we need to look at the limit as x approaches 2 of f of x. And because this is a rational function, we're going to do a little bit of working on manipulating this algebraically. I see that I've got a function that I can factor. So I'm going to go ahead and do that. X squared plus 6x minus 16 can be factored as x plus 8 times x minus 2. And that's going to be divided by x minus 2, which means that the x minus 2's can divide and make 1. And now I have a function that it doesn't break if I plug in the 2. I'm not breaking math anymore. So if I plug in 2, I get 10. And now for part 3 of the continuity test, we want to make sure that f of 2 is equal to 10. And since f of 2 is equal to b, that means that b has to equal 10. And as long as b equals 10, our function is continuous everywhere. Okay, in piecewise function, this is one that has a parameter, and this is not going to be a removable discontinuity, but we have a parameter that is like a constant as part of our definition. Again, looking at the continuity test, you're going to want to make sure you think about whether your function exists even. If it doesn't exist, then you're going to have trouble making it continuous. But the big thing with these piecewise functions is you're going to want to make sure that the limit of both pieces matches, that if you take the limit as x approaches the value from the positive and the negative direction, you get the same number. Otherwise, your piecewise function has a jump discontinuity in it, and you want to make sure it doesn't if it's going to be continuous. So the way we're going to do that, here's an example. So if I think back again to part 1 of that continuity test, f of, well, first of all, cosine is continuous, and a linear function is continuous everywhere. So the only place where we might have some trouble is at pi. So we're going to say, well, f of pi, I know for sure, is going to follow this second part of the piecewise definition. So f of pi is going to be negative pi plus a, because that's where the equal to bar is. Okay, now I'm going to look at the second part of the continuity test, and the second part of the continuity test is the one where we want to make sure that we're very clear in our notation. We're going to take the limit as x approaches pi from the negative direction, and if I'm coming at pi from the negative direction, I would use the top half of that definition. So it'd be cosine of pi, which is negative 1. And then if I take the limit as x approaches pi from the positive direction, I'm going to get that parameter involved because that would be negative pi. Oops, I'm going to rewrite that a little bit better. Negative pi plus a. And now if I think about part 3 of our continuity test, we have to make sure, actually we're still on part 2, back up, sorry. In order for this limit to match or exist, then those two pieces have to be equal to each other. So negative 1 has to be equal to negative pi plus a, otherwise our limit won't exist. So in order for that to be true, a has to equal, add pi to both sides, pi minus 1. Okay, now just to double check, is it true that f of pi is equal to the limit, which we know is negative 1? And so we could go back and say, well, if it's true, then negative pi plus a, which is pi minus 1, is equal to negative 1. And yes, that's true. So if we do, as long as a is defined as pi minus 1, this function is continuous everywhere. Make sure you're supporting your work with the correct notation. Make sure you show that you're doing limits here. Don't just say cosine of pi equals negative pi plus a, because I don't know where those came from. All right. I would recommend that you try this one without me, and then I'll talk through it. Again, go back to that 3-part definition, but you have now 2 values of x that you need to worry about. You need to worry about negative 1 and 1. You don't have to worry about anywhere else because this is linear. Linear functions are continuous everywhere. This is a quadratic. Quadratic functions are continuous everywhere, and this one's also linear. So I don't have to worry about in between the joining places, but I do need to worry about negative 1 and 1. Okay, so if I look at f of negative 1, that would use the middle part of the definition. So negative 1 squared is 1 plus a minus b. Now if I look at that second part of the definition, the limit as x approaches negative 1 from the negative direction of f of x is going to be negative a, and the limit as x approaches negative 1 from the positive direction of f of x is going to be that middle part of the definition again. So 1 plus a minus b. Those two things have to be equal to each other in order for that limit to exist, so I'm going to go ahead and set those things equal to each other. So negative a has to equal 1 plus a minus b. And I don't know how to mess with this, but I still am going to have a's and b's in it, right? So I could add a to both sides. So I'm going to say b, I'm going to add b to both sides and add a to both sides. So b is equal to 1 plus 2a. And at that point, I'm kind of done. Like, that's all that gives me. So then I'm going to go back to the other place where this function might fail at 1. So f of 1 would be, again, middle part of that definition. So 1 plus a minus b. And then I'm going to go to the second part of the definition. So the limit as x approaches 1 from the negative direction. That would be the middle again, so that'd be 1 plus a minus b. I'm going to get rid of my face so there's more room. And then the limit as x approaches 1 from the positive direction would be 1 times x, or 1 times b, because x is 1. Those two things have to be equal to each other, so we're going to set those two things equal to each other. So I have b is equal to 1 plus a minus b. So 2b is equal to 1 plus a. Okay, so now I'm looking at, well, I've got a's and b's here. If b is equal to 1 plus 2a, then 2b would be double that. I need some more space. I'm going up here. So 2b would be 2 times 1 plus 2a has to equal 1 plus a. So 2 plus 4a equals 1 plus a. So a is equal to, well, 3a, is equal to negative 1. So a is equal to negative 1/3. And now I'm going to figure out what b is. I'm going to use this piece of the puzzle. So b is equal to 1 plus 2 times negative 1/3. So b is equal to 1/3. And as long as those two parameters are defined as negative 1/3 and 1/3, then our function is continuous everywhere. All right, so that's the technique with these problems. Please make sure when you're doing these problems that you're really clear about your notation, that what we're really doing here is we're doing limits. So when we set these things equal to each other, it's because we have done limits to get there. Make sure you have that notation in there. All right, good luck.